A happy day of learning to you, my dear students. Let's start our day with an exciting lesson for today. Are you too excited? Are you too squared? Just kidding. So let's start our lesson today. So our topic for today is all about the sum of two squares. So let's first read our objective for today. So by the end of this module, you, students or learners, will be able to first determine whether a number can be expressed as a sum of two squares. Second is understand the role of primes of the form 4k plus 3 in this determination. And the third is find actual integers a and b such that n is equal to a squared plus b squared. But first, before we start our lesson, let's have first our drills. So let's have our warm up exercises. So I want you to identify the perfect squares in these numbers, in this set of numbers. First, find the squares in this set of numbers 1, 2, 4, 7, 9, 10, 16, 20, 25, 30. Have you already found the answers or the numbers that are perfect squares? Let's find out if your answers are correct. So, perfect. Very good. You found the correct answers. So, perfect square numbers on the set of numbers given are 1, 4, 9, 16, and 25. Next exercise is I want you to calculate the square roots of these given set of numbers. What is the square root of 16? What is the square root of 25? What is the square root of 36? What is the square root of 49? And what is the square root of 64? Have you already found your answer? If yes, then let's check if your answers are correct. Yes, very good. Your answers are correct. The answers are 4, 5, 6, 7, and 8. Very good learners, students. Now, let's continue and dive through our discussion. Let's first define what is the sum of two squares. So the definition of sum of two squares is a number n is a sum of two squares if there exist integers a and b such that n is equal to a squared plus b squared, where n represents any number. So for example, 5 is equal to 1 squared plus 2 squared. That is because 1 squared is equal to 1 and 2 squared is equal to 4. So 4 plus 1 is 5. Next is 13. So 13 is equal to 2 squared plus 3 squared. Why? Because 2 squared is 4 and 3 squared is 9. So 9 plus 4 is 13. And last example is 50 is equal to 5 squared plus 5 squared. So 5 squared is 25 and 25 plus 25 is equal to 50. That is the sum of two squares and its examples. Let's proceed. So these are the steps in finding the sum of two squares or identifying whether a number is a sum of two squares. So step 1 is factor the given number. So every number can be written as a product of prime numbers. So any number to have a unique prime factorizations or prime factors. Like for example, 45 has a prime factorization of 3 squared times 5. So 3 squared is 9 times 5 is equal to 45. Next is identify the primes of the form 4k plus 3. So divide each prime by 4. If the remainder is 3, it's 4k plus 3 type. So like 3. So 3 divided by 4 is 0 and its remainder it's 3. So it's a 4k plus 3 type. So let's proceed. So check if the exponents is an even number. So there's a rule in this one. So it's the Fermat's theorem, sum of two squares. If a number can be expressed a sum as two squares if and only if every prime of the form 4k plus 3 appears with an even exponent. Otherwise, if a 4k plus 3 prime has an odd exponent, you stop the solution immediately. So there is no sum of two squares in that given number. So I don't want you to be confused. So if a number has a prime factorization and its prime factors do have a 4k plus 3 with an even exponent, you continue. But if the 4k plus 3 has an odd exponent, stop. But if you found the prime factorization numbers of a certain number, which is 4k plus 1, it's okay for it to have an odd exponent. It is only exclusive for the 4k plus 3 that the exponent should be even. So 4k plus 3, its exponent should be only even. And on the other forms like 4k plus 1, it is okay that its exponent are odd, either odd and even. So next, let's represent the known primes up as sums of squares. So we have the here 5 is equal to 1 squared plus 2 squared. So we're just going to break it down as a smaller sums of squares. So 1 squared plus 2 squared is equal to 5 because 1 squared plus 2 squared, 4 plus 1 is equal to 5. Now we have here 13 is equal to 2 squared plus 3 squared in the previous given, which is 2 squared is equal to 4 plus 3 squared is equal to 9. 9 plus 4 is equal to 13. So is that clear? So I hope everything is clear. So 17 is equal to 1 squared, which is 1, plus 4 squared, which is 16. So 16 plus 1 is equal to 17. So we have here a tip. So for 4k plus 3 primes with even exponent, you can write it as p squared is equal to p squared plus 0 squared, where p is your prime factor number. So, like on the previous slide, we have here our 3 as 4k, 4k plus 3 type. So you can express it as p squared is equal to p squared plus 0 squared, which is p is equal to 3. So 3 squared is equal to 3 squared plus 0 squared. So it is 3 squared is equal to 9 plus 0 squared, 0. 9 plus 0 is equal to 9. So after determining your smaller sums of squares, use the Brahmagupta-Fibonacci identity, which gives us a formula of a squared plus b squared multiplied by c squared plus d squared is equal to a multiplied by c, positive negative b times d, the product squared, plus a d minus plus b c squared. So combine two numbers already expressed as sums of squares. Repeat if necessary for multiple primes. So I hope everything is clear on our steps. So 45 is equal to 3 squared plus 6 squared. using our steps. So 3 squared is equal to 9 and 6 squared is equal to 36. So 36 plus 9 is equal to 45. So 45 is the sum of two squares. So I want you to try example number 1. So example number 1, 45. So 45 is, we have our answer, but I want you to try this one on the process. So let's try on our whiteboard. So we want to find 45. So 45, its prime factors are equal to 3 squared multiplied by 5. Sorry for the bad writing. So 45 is equal to 3 squared minus 5. So those are the prime factorization. So identify primes of the form 4k plus 3. So 3, as we discussed earlier, is a 4k plus 3 type. It is, so using the modulo rule, 3 is congruent to 3 mod 4. So it is a 4k. It is a 4k plus. It is a 4k plus 3 type. Next is 5. 5 is congruent to 1 modulo 4. Why? Because if you divide 4 by 5, it is 1, remainder 1. So it is a 4k plus 1 type. So 4k plus 3 type has a rule that in its prime factorization form, it should have a even exponent. So it has an even exponent. So you will proceed. 5 is a 4k plus 1 type. It has an odd or either even exponent. You will continue or proceed. So let's proceed, no? Now let's proceed on the present the prime form the factors as a smaller sums of squares. Now 3 can be expressed as 3 squared plus 0 squared. Like on our form, p squared is equal to p squared plus 0 squared. Any 4k plus 3 type with even exponent. And 5 can be represented as 1 squared plus 2 squared. So I hope everything is clear from step 1 until step 3. So let's recall step 1 is from factorization, which is 3 squared minus 3 squared multiplied by 5. Next is identify the forms park a plus 3, and 3 is a form of park a plus 3 with an even exponent. And um, express this as smaller sums of squares. So we have here our 3 squared plus 0 squared is equal to 3, and 1 squared plus 2 squared is equal to 5. Now use the Brahmagupta Fibonacci identity. So our A here is 3, B is 0, C is 1, and D is 2. So A, B, C, D. Now let's proceed on our formula. So our formula is a squared plus b squared times c squared plus d squared is equal to a times c plus b times d squared plus a times d, sorry for the writings, minus b times c squared. But I hope you can get the concept and writing it also on your paper. So let's substitute. So our a is 3, so 3 squared plus our b is 0, 0 squared times c is 1, 1 squared plus d is 2, so 2 squared. Now substitute it in our formula. A is 3 times 1 plus 0 times 2 squared plus A is 3 times 2 minus 0 times 1 squared. So this gives us 3 times 1 is 3 plus 0 times 2, 3 times 0 plus 0. 3 plus 0 is 3. So it gives us 3 squared plus 3 times 2 is 6 minus 0 is 6. 6 squared. So 45 is equal to 3 squared. So 45 has a sum of two squares, which is 3 squared and b squared. So I hope everything is clear. Any questions, clarifications, final reactions? Nakakasabay, nakakasabaw. Hope you get it all. Now, I want you to answer it on your own using our steps. So example number 2, 117. First, you get first step is prime factors. So its prime factors are 3 squared and 13. Next is identify the 4k plus 3. So it has a 4k plus 3 even exponent and 13 is equal to 2 squared plus 3 squared. Next is express it into sums of two squares. 3 squared plus 0 squared and 13 is 2 squared plus 3 squared. So 3 squared is 3 is our A, 0 is B, 2 is C, D is 3. And then put it in our formula. So 3 times 2 plus 0 times 3 squared plus 3 times 3 minus 0 multiplied by 2 squared. So our answer is 6 squared plus 9 squared. So t prime, the sum of two squares of 117 is 6 squared plus 9 squared. So try this, example number 3, 693. Its prime factors are 3 squared times 7 times 11. So it cannot be a sum of two squares because its prime factors are 4k plus 3 type but has an odd exponent. So I hope you learned many things and you've enjoyed solving on our lessons for today. I want to leave you a task and I want you to solve it on your own for practice and for your more improvement. So before we end, I want to leave some tips regarding on our sums of two squares. So first is always factor. That's the key step. Memorize small primes as sums of squares such as 2, 5, 13, 17, so on and so forth. For form 4k plus 3 primes with even exponent, you can write it as p squared plus 0 squared like 3, which is 3 squared plus 0 squared. And use identity step by step. Don't try to guess. squares for big numbers. So I hope you learned many things for today and you enjoy our topic. So see you again and God bless and always be too excited not to square. Bye learners.